Hello friends, welcome to Masters Online Classes. Today we are going to discussing about the main chapter in plus 2 physics, that is moving charges and magnetic effect of current. First we have to understand what is a magnetic field. We all know a bar magnet, correct? A bar magnet is a material which produces what? Magnetic field. Okay, that is, please suppose this is a bar magnet, consists of two poles, north pole and south pole. North pole and south pole. So when we introduce a ferromagnetic material towards any pole, it make it attractive. Correct? So this is the attracting property known as what? Magnetic property. Because there is a field around this bar magnet. So this is known as magnetic field. Okay. Magnetic field. Then what is the unit of magnetic field? The unit of magnetic field is Tesla. Okay. Unit of magnetic field. Unit of magnetic field is Tesla. T-E-S-L-A. So we'll write as capital T. Okay. Next. Consider a current carrying conductor carrying I amperes of current in this direction. So we have to find the magnetic field at a point P, which is the distance R from the conductor. Okay, this is one of the famous law in moving charges and magnetism, that is Biot-Savart's law. Okay, Biot-Savart's law. Biot-Savart's law, a famous law. The necessity of this law is used to calculate the magnetic field. Correct? So a current carrying conductor produces a magnetic field. We know a current carrying conductor produces what? Magnetic field. So what is the direction of magnetic field? Yes, the direction of the magnetic field is given by right hand thumb rule. Suppose a person's thumb, right hand such that the direction of the thumb indicates direction of current and the direction of the curved finger indicates direction of magnetic field. Okay, so this is what the direction of magnetic field is to be assumed. So imagine if current is going in this direction, what is magnetic field direction? Yes, we have to place like this, correct? We have to place like this. So thumb indicates direction of current and curved finger, yes, into the board. So this is the direction of magnetic field. Correct? If the direction of current is reversed, what happens? Suppose if the direction of current is like this, downwards, what is the direction of magnetic field? Yes, we have to reverse this. Look. Yes, downwards, direction of current is downwards. So this curved finger going, yes, into. Okay, so two different points, two different current carrying conductors in different directions of current, so magnetic field is get reversed. The same thing happening here. When current is in this direction, what is the direction of magnetic field? This is the direction of magnetic field. So this is the direction of magnetic field. So here magnetic field is into the board. Correct? Next, we have to calculate what is the value of the magnetic field. What is the intensity of the magnetic field? We know the direction of magnetic field is into the board. We have to calculate the value of the magnetic field. That is defined by, yes, Biot-Savart's law. This law states that, okay, consider the full length. In that, consider the portion dl, a small portion, okay, dl. Due to this dl, what is the magnetic field here? We know a current carrying conductor produces a magnetic field. Here we consider only a small portion dl. Due to this dl, there is a magnetic field dB. Small length, small magnetic field dB. So dB, magnetic field dB is proportional to. It depends upon what are the parameters. Yes, IDL, current element IDL. So dB at this point is dependent on IDL. This is current element IDL. Then sine of the angle between the line joining the conductor and the external point. This is the external point, this is the conductor. So this is the imaginary line joining the conductor and the external point. That is theta. So it is proportional to sine theta, and it is inversely proportional to, yes, the distance. Because if this is the conductor and this is the point, this is the magnetic field. If the point P is at a very large distance from the conductor, what happens? Yes, the magnetic field gets reduced at that point. Okay, so this is inversely proportional to square of the distance. This is what magnetic field relation. So we have to compare, we have to conclude that so dB is proportional to IdL sin theta upon r square. So we have to introduce a constant. To remove the proportionality constant, we will introduce a constant, that is k, and the value of k is mu naught by 4 pi. So dB is equal to mu naught by 4 pi IdL sin theta by r square. So for a current carrying conductor, this is the magnetic field. For small element dl, small magnetic field dB. For entire length, we have to multiply with what? Yes, yes. So this is what Biot-Savart law. Next, the statement for Biot-Savart law. So earlier we discussed how it happens. The law states that the magnetic field due to a current carrying conductor is directly proportional to current element IdL. Current element IdL. Sine of the angle between the line joining the conductor and the external point. Where we have to find the magnetic field up to that. Okay, so there is an imaginary line. So theta is the angle between the conductor and the line joining. Then next, the magnetic field is inversely proportional to square of the distance between them. That means when the distance increases, magnetic field at the point where we have to determine decreases. Okay, so this is the conclusion. So dB proportional to ideal sin theta by r square. So in order to remove that proportionality constant, proportionality sign, introduce a constant, mu naught by 4 pi is the constant, and dB is equal to mu naught by 4 pi ideal sin theta by r square. Okay, so what is this mu naught? This mu naught is what? Permeability of the free space. Okay, because we are doing this experiment in free space, so mu naught is the permeability of the free space. Okay, how much magnetic lines of force passing through that free space. Okay, and there is a relation between this mu naught, that is mu r is equal to mu by mu naught. Mu r is equal to mu by mu naught. So mu r relative permeability is equal to permeability in medium upon permeability in free space. And next, what is the value of this mu naught by 4 pi? This is having a constant value, that is mu naught by 4 pi. Mu naught by 4 pi is equal to 10 raised to minus 7. So this is what up to Biot-Savart law. Next, force acting on a charged particle moving in a magnetic field. Okay, consider this is a magnetic field. This cross indicates magnetic field is into the board. Okay, the magnetic field is into the board. Consider a charged particle which is moving perpendicular to a magnetic field. Okay, so we are taking an electron. So consider this is an electron. So this electron moves in this direction with some velocity v. Okay, you have to understand, when a charged particle moving perpendicular to a magnetic field, surely it will experience a force. Okay, a charged particle moving perpendicular to a magnetic field experiences a force. Look, this is the direction of magnetic field and this is the direction of movement. So what is the angle? 90 degree perpendicular. So it will experience a force. So due to that force, it will move in a particular direction. So what is the direction? That is given by Fleming's left hand rule or right hand palm rule. Okay. So this has a velocity v, and I will write that rule. Fleming's left hand rule. Fleming's left hand rule. So this rule indicates this Fleming's left hand rule. This forefinger indicates direction of magnetic field. Middle finger indicates direction of velocity of the charged particle, and thumb represents direction of motion of the charged particle. So here, magnetic field is into the board, so into the board, correct? Into the board. And what is the direction of charged particle? That direction, yes. So the middle finger indicates direction of charged particle, and thumb represents direction of force. So in which direction it will move? Yes, upwards. So this charged particle is pulled upwards. Okay, so it will move in this direction. So there is a force which exerts on the charged particle, so it will move upwards. Due to that force, it will tilt its direction. So it will move in this direction with a velocity v, the same velocity. And what is the direction of force? Again, magnetic field, velocity, and thumb direction of force. So it will move, yes, in this direction. So this is the direction of force. Again, it is pulled. Yes. So collectively it will execute a circular path. It will execute a circular path. So a charged particle moving perpendicular to a magnetic field experiences a force, hence it moves in circular path. Okay. So that is what force acting on a charged particle. So F, that force is proportional to V sin theta. Force vertical component of velocity is proportional to V sin theta, and that is proportional to, force is proportional to, magnetic force is proportional to charge, magnitude of charge, then that force is proportional to S, B. So these three components depends the force, depends the direction of the particle. So we collectively will write F is equal to B Q V sin theta. This is the force experienced or force acting on a charged particle moving perpendicular to a magnetic field. So you can surely say what is the direction of the charged particle moving perpendicular to a magnetic field? Yes, circular path. Okay, so a charged particle moving perpendicular to a magnetic field experiences a force, hence it moves in circular path. And the direction of the force is given by Fleming's left hand rule, or another rule, right hand palm rule, or right here, or right hand palm rule. Right hand palm rule. So right hand palm rule says that, so imagine a person's right hand such that the direction of the forefinger, this forefinger indicates direction of magnetic field, and thumb indicates direction of velocity or direction of movement of charged particle, and this vector indicates direction of force. Clearly we can use this law here. So this is the direction of what? Charged particle with a velocity from here to here. So we have to place our thumb in this direction. Correct? This direction. Thumb in this direction, because the charged particle are moving in this direction. And what is the direction of magnetic field? This forefinger into the board. Yes, correct. So magnetic field is into the board. Velocity is in this direction, and this indicates, the center point of the palm indicates direction of force. This force is upwards, so the direction of force is upwards. So in each instant, the force is acting like this into the, yes. So this is the direction of force. So the direction of force we can find using the two rules, Fleming's left hand rule or motor rule, then right hand palm rule. So this is the expression for magnetic force. F is equal to BQV sin theta.